is it's a new vulnerability. Like all the router vendors had this issue because they all made the same mistake, sure. And so this is very widespread, and SNMP v3 is standardized as the control protocol for lawful intercept. Now, this is what we call Schäuble routing. This is where you can this is where you can tell a switch or router to actually mirror a port or give you parts of the traffic that someone else is sending from A to B. And, well, those control messages are used to send them to the router and tell it, like, do this or don't do it. And they're designed so the system administrator cannot see this activity. This is really bad. Because all the routers in the internet need to talk SNMP, and it's really hard to maintain an access list on all interfaces for this. So, this is right now the biggest threat to Cisco security, because of course they had this code issue. And you can essentially become your own Bedarfsträger for certain network traffic engineering that you have in mind. And then there is binary exploitation. Binary exploitation on Cisco hasn't seen so many published exploits. You can classify them essentially into pieces. One are service vulnerabilities, like services that the router offers. They're obvious places to look for vulnerabilities, but they're also unlikely to be in production networks. Like nobody with a sane mind runs an FTP server on a Cisco, except for having a very fancy place to store their porn. And then there is router protocol vulnerabilities. Those are interesting because the router needs to talk them. So an OSPF exploit is a lot more interesting than an HTTP overflow. Now, what do we have on the detection side? First of all, we have the very same mechanism that I just mentioned to be really broken, SNMP. This is what all people use for management. So it's a polling mechanism, but it's based on the MIPS, which is a database. And those MIPS are designed for network monitoring. So you can see how many packets go in and out and how the routes look and stuff like that. You can't see how many processes have I running. Did I get a new one? Did I get one that opens support? Stuff like that you can't see over SNMP. Syslog, on the other hand, is free-form messages, so you can actually get debug information out, but it's too slow and rarely used. So one of the actually quite useful detection and monitoring sites is config polling. There's tools like Rancid that actually go ahead and take all your configurations from the routers and diff them and analyze them and tell them when you got a new user, because that's usually of interest. For routing protocol attacks, the people are pretty much well placed. They have route monitoring. They see when the routing changes dramatically, so that is actually not a problem. Surprisingly enough, traffic accounting is actually a very useful source in network forensics, because people that route traffic, like ISPs, actually happen to have traffic accounting really well figured out, because that's what they get paid for. So they actually have detailed data on this. And it is quite useful to know who talked to whom at what point in time when you have an intrusion case and you try to figure out where they came from. So when we look at the types of attacks and then what we have in terms of defense, we look pretty naked on the binary exploitation side. And so since I constantly fail to come up with like weaponized Cisco exploits, I figured, nah. Well, the other approach is do the HoneyNet way and like build something to catch everyone else doing it. So we started looking into this. Because the common solution is try to lock everything centrally, with, even in a worst case, with debug messages, which are really slow and which actually stop the router while they're printed. So this is not good for performance. And then, of course, you need someone to actually parse those logs manually, because every single iOS version changes the output format, so you can't actually use a decent Perl script. Or SNMP, as I just already said, they just don't have the information you're looking for. Also, trying to detect exploitation while it happens, like in the moment the exploitation happens, has proven to really, really suck as an approach. It has been tried many, many times. Many of you probably have some fancy piece of software installed on their laptop that kind of like says IPS or something. But it's really, really hard. What you actually detect is what people did after they got a stable code execution. So there is another source of information that we can look at, which is the crash info file. Some iOS versions, later iOS versions, write a text file called crash info that contains memory dumps and register dumps and all that. It is meant for iOS coders, obviously, to figure out what they fucked up. The problem here is that in about 80% of all the cases, it is entirely misleading. Now, here's the thing. If you ever did any binary exploitation, you probably notice if your traceback says 4242440, then something very desirable happened. The problem is with this. If an iOS crashes due to, for example, Stack Overflow, as it is here, it has a race condition, because the crash writer process tries to figure out what process actually crashed. And the analysis seems to be written so badly that he always ends up with himself. Which is why you see crash writer down here. What I found most amusing is in the latest iOS versions that I've seen, you can configure an arbitrary delay by hand. So they probably figured, we have a race condition, we have to wait some time. We have no idea how long, so leave it to the administrator. So what will those binary exploits actually do? They will actually patch the system in pretty much most cases. They want the router to no longer validate the passwords. They want the router to no longer lock. And they probably don't want the router to use any firewall functionality whatsoever. It is likely that this patching is actually going to be in the data structures and not in the code. The code is the more reliable place to do it, but the data structures are a lot harder to detect. Like, you can patch out the code that verifies your password, or you can set the VTY to authenticate it already. The latter is harder to do, but harder to detect. And they will probably also terminate processes. But we're coming back to this. So for detecting this, we actually need, what every forensics session actually needs, is we need a way to acquire our evidence first, and then recover information from that raw data, and then, make a more or less educated decision on what we see. Looking inside iOS, it's essentially the biggest LS program you've ever seen. It's one large ELF binary, and statically linked. It's loaded by a kind of BIOS called the ROMmon, and it runs directly on the CPU. There is no fanciness involved. There is a little bit virtual memory mapping, just as much as they need. They are not using any privilege levels of the CPU. Processes are actually not really processes. They're threads. They have a CPU context, and that's about it. So every process can write in everyone else's memory space because they all share one, which makes it interesting. They have a fucked up multitasking, but we don't care about this too much. What we care about is they have system-wide data structures because they're one piece of software. They have one common heap. And they have very little abstraction around the data structures, which is actually the reason why it's so easy to fuck it up, because you're writing C. And if you're addressing the wrong pointer, and the pointer was actually a string or something else, it's really easy to have a string that turns out to also be a mapped memory area, and then you're writing somewhere in the memory without noticing. iOS boots actually from the ROMmon. It will load the image from Flash or network. Nobody does that. It may be self-decompressing, and it may actually carry additional firmware with it. So this is important for the analysis, that you're not surprised to actually see code that is not for the CPU platform your Cisco is for. The configuration is also loaded in text, and it's parsed on load. So you can actually have a wrong configuration. You could actually have a poem instead of a configuration stored on iOS. It will just line by line tell you that it doesn't understand it while booting. And if your poem would include the word shutdown, it would probably shut down an interface. The defaults that it applies if it doesn't load any specific information from you differ in every image, and there is no way to get them out. So the same configuration on a different machine does something entirely different. Everything is kept in RAM, which is a problem for evidence acquisition. Because on regular common operating systems, the stuff you want to see, the stuff you're after in forensics first is non-volatile. So you take the hard disk. For iOS, that makes no sense, because all the information you want to see is volatile. So we need memory imaging, and we need memory imaging on demand, or if the device actually restarts, because that's the default behavior. If you are one big program and something goes boom, you pretty much have no option, because you have no idea what data structures are corrupted in what way. So you have to reboot the box, which is the default behavior, which sucks for evidence acquisition, because all the evidence just went out the window. So luckily, we also have some non-volatile evidence, but that's not really useful, because nobody would write into the NVRAM or change the configuration if they have a binary 0-day. Luckily, iOS coders have the same issue. So the boxes can actually write cores. They write a flat memory dump core, actually multiple cores, one for the main memory and then for all fancy memory that they have an individual one. And it's a perfect evidence, because it's a raw memory dump. There is no interpretation whatsoever. So the only thing we need is we configure the box to do it, because by default they don't do it. And I talked to many service provider people and large network people, and they all told me none of our boxes write core. For two simple reasons. The default behavior on failure is reboot, so they're not rare. So the boxes are optimized so they boot as fast as they can. So if they write core before they boot, it takes longer, and someone is going to notice the network outage, which is what they have redundancy for, but anyway. And also, well, it wasn't really useful for anyone except for iOS developers with an analysis tool that they supposedly have, and for exploit writers, because you could see where your stuff ended up. So we wrote a core dump analyzer, which takes raw core dumps and iOS images that were supposed to run on this router, and analyzes them based on the information in the image and what we know about Cisco. We have actually written this thing in .NET because I like .NET, and I didn't want to do the N-case stunt of like getting owned with a corrupted file system. So this is why we're not using C. Now the thing is, the first thing that comes to mind is, well, if someone gets code execution and you write core, then he's just patching the core writing functionality and you're out. That is correct. So we also support memory acquisition over the GDB protocol, which is another developer feature unintentionally left in. So the boxes speak in the serial GDB protocol, which you can then use over the serial console to actually acquire the memory. It is very painful. Even more painful, but actually not patchable by any shellcode, is you break into the ROM-mon, into this kind of BIOS, and hex dump the entire machine, and then compile it back into binary. Be surprised, it works quite well if you got enough time. So, What do? We take the iOS image that was supposed to run on the router. So you should not actually copy the image down and then compare it to the core dump, because that would be the same thing. So we're expecting that you have a uncompromised copy of your image, or that you can legally or less legally obtain one from the Cisco FTP server.